Is it okay to go ahead and get started?
Yes, we can get started. Do you want that we turn off the cameras?
If anybody is willing to turn their cameras on, I'm definitely keen on that. It's always good to be able to talk to people.
Yeah.
Great, thank you very much, everyone. Okay, great. So we're back for day 2 of Variational Bayes and Beyond, and I just want to do a quick recap before we dive into where we left off. And so before I go forward, my understanding is that you all have access to the slides from day 1 now. If you haven't already seen those, they're also at the link below, but I think that they have been distributed to all the participants. So let's just talk about where we were yesterday. So one of the big things that we spent some time on is saying, Bayesian inference is used in some extremely important applications in science and medicine and engineering and the social sciences, really up to like the present moment. And one of the situations that people find themselves in, these scientists and engineers and social scientists, et cetera, is that they want to do Bayesian inference. They want to do it quickly. They want to do it quickly in compute time. They want to do it quickly in user time, and they want to do it quickly, and they want to do it accurately. They want to get accurate results when they're doing that. And so we're essentially sort of exploring variational Bayes as a potential way to do this, to do approximate Bayesian inference, which we spent some time on yesterday. And so the one thing that I want to just go over from the slides yesterday, which hopefully you are sort of familiar with and remember, but let's jog our memories a little bit, is the choices that we had made. So we went in saying we want to do this approximate Bayesian inference. We have to approximate things because we have these sort of large high-dimensional models, and we can't just solve them in closed form. And so in particular, we want to get this posterior. And we're thinking of it here as a function of theta, the unknown parameter, and we've been given some data y, and remember y represents sort of all of our data, everything that we've seen. And we're going to approximate that posterior with some distribution. We call it Q star. That's just whatever we're approximating it with. And that was sort of the first choice that we made. That's a choice to approximate the posterior that way. And then we said, well, the particular form of approximation that we're going to explore today is optimization. We're going to say that Q star is the closest of a set of nice distributions, that's capital Q. So that should be distributions where we can get the things that we want out. So let's say, means or variances for our point estimates and uncertainties. And F is some notion of farness. And we're explicitly not using the word distance because the types of things that we're going to be using aren't always distances. But some notion of farness between our approximation Q and our exact posterior P. And this is a choice. You could use Markov chain Monte Carlo, and that would not be an optimization problem. And then we made a further choice. We said, well, let's use a particular notion of farness to help make this a well-defined optimization problem. Let's use the KL divergence, the Kullback-Leibler divergence, in a particular direction, this direction in particular. And we spent some time justifying that, saying that it was a convenient choice. And now we want to ask, does that convenient choice do the things that we want it to do? Of course, you could make other choices here. A number of people brought up other choices in the chat that you could make. And I think that's a really interesting direction and one we'll spend a little time talking about. But something that we saw was that KL, and in particular KL in this direction, is pretty convenient because it gets rid of that normalizing constant, which sort of makes this otherwise a chicken and egg problem and a difficult optimization problem to solve. Okay, so then we said, what's a nice distribution? Well, there are lots of things that you could say are nice distributions. It just has to be some distribution where you can get out what you want. And here we're saying we want point estimates and uncertainties. This might take the form of means and variances. Certainly that's our focus today, but that doesn't have to be your focus in general, but it's certainly a common focus. And in that case, we might use so-called mean field variational Bayes. So here we assumed that the distributions that we're using as our nice distributions, factorized, so our approximating distributions. We're not making assumptions on the model, on the prior unlikelihood, just on the approximation. And we pretty much always in practice assume that actually Q is in the exponential family. If you ever find something where somebody says, oh, we assumed everything really general and we're just assuming this, factorization assumption, I think you'll probably find at the end of your derivations that in fact, everything worked out to be in the exponential family. Okay, so then finally, we have to solve this optimization problem somehow. And there are many ways to do that. These are just some examples. You could use coordinate descent. You could use what's known as stochastic variational inference. You could use automatic differentiation variational inference. I haven't defined SVI and I haven't defined ADVI. I'm just sort of saying, once you have an optimization problem, you can use modern optimization problem machinery and you can get something out here. So this is just to say you can solve this optimization problem once you've set it up. And so now what we want to spend some time doing is we want to spend some time saying, hey, does this even work? You know, this mean field assumption is pretty strong, this factorization assumption. Certainly we would never want to make it about our actual model that we would have this factorization assumption. And so we want to ask, is this a reasonable assumption? Does this ever give us anything useful? And we're going to spend a little time basically looking into that right now. Okay, so let's start with some examples. I'm going to start with a simple sort of like very simple two-dimensional example that's so simple specifically so that we can actually look at what's going on, that we can actually view what's going on. And then I'll move on to some real data, more complex examples that I think are more representative of what you would encounter in real life. Okay, so particulate matter is actually a super important and relevant application area, even if the example we're going to look at is pretty simplistic. So here what we're going to be looking at is we're going to be looking at so-called PM 2.5. So this is a big deal in terms of air pollution. It has been for a while. There's also reason to suspect that PM 2.5 particulate matter might interact in some way with COVID, and so we care about it for that reason as well. But really, it's just a big deal on its own. So PM 2.5 means the mass per cubic meter of air of particles with a size or diameter generally less than 2.5 micrometers. It's also known as fine particulate matter. It's 1/400th of a millimeter. And this picture that we're seeing here is Bangkok. And you're just seeing that, you know, there are a lot of cities in the world that have some amount of air pollution. And this is something that we'd like to understand. What is the amount of PM 2.5? So we might collect a bunch of sensor readings of log of the concentration of PM 2.5 in the atmosphere. So let's imagine that's our data here. So we have N, capital N sensor readings, Y1 up to YN. Y is again just our collection of data, all of our data. And what we're doing is we're trying to figure out something like what is the actual PM 2.5 concentration at wherever our sensor is. And maybe we also don't know what our sensor's noise is. Maybe it's a noisy sensor and we'd like to learn that as well. And so that's what this model encodes. So here, theta, our parameters, our unknowns, are exactly this. We don't know the mean of PM 2.5, which we imagine is the sort of actual concentration of PM 2.5 at this location. Let's call it mu. And we don't know the noisiness of our sensor. Let's call that sigma squared, the variance of our sensor. And so our model, our likelihood is what type of data would we get out if we know that our sensor, say, is normally distributed in its noise, if it has some mean of mu and some variance, sigma squared. And so we would like to know that mean and variance. Now, I said here we're not going to focus so much on choosing the model. We could spend like quite a lot of time. We could spend a whole course on model choosing. So let's imagine that a scientist came by and said, here's a reasonable prior for this model. So in particular, A naught, B naught, mu naught, and lambda naught here are all constants that the scientist has told us. We know them. We know these constants. Now, something that's interesting about this model is that this is what's called a conjugate prior. So you could actually take this prior and this likelihood, and I think it's a really good exercise if you don't immediately know how to do this to find the posterior. You can write this posterior in closed form. And so I want you to just take a second and think, wait, I thought the whole point of this talk was to figure out what is our approximate posterior. So why are we looking at a problem where we know the exact posterior? Does anybody have any thoughts about that? Why would we look at a problem where we can actually calculate the exact posterior in closed form? Okay, so I think there's a point in the chat, and I think this is what this is getting at exactly. It's validation. So at the end of the day, I'm going to run my algorithm, my approximate Bayesian inference algorithm. Maybe it's variational Bayes, maybe it's something else. You know, it doesn't matter for the moment. Just suppose it's some approximate Bayesian inference algorithm. If I don't know theoretically, that it always returns exactly the right answer, how do I know that it returned the right answer? And so one way to get around that is to know the answer and then check against the right answer. And so this is a case where we know the exact posterior, and so we can check if our approximation is good. And I think something you want to be thinking in the back of your mind is, well, eventually we're not going to know the exact posterior. I mean, that's the whole point, right? Is to use this in cases where we don't know the exact posterior. And so just be thinking in the back of your mind, well, how are we going to check that? Or do we need to check? What's going on there? Just keep thinking that. Okay, but in this case, we can check. And that's specifically why we've looked at this problem, is it's a case where there is a ground truth. So we're going to look at that. Now, something I'll just mention, I'm not going to go through derivations here, although I think, again, this is a useful exercise to do in sort of the privacy of your own home later. And if you do some of the derivations that we're going to run through here, it's much easier to work with, instead of the variance, 1 over the variance, which is known as the precision. And so all I'm going to do is I'm going to take this exact same model and I'm going to replace all the variances with 1 over the variance for the precision. So this is exactly the same model, it's just slightly reparameterized. It just turns out that pretty much everything in life is easier to do with a precision, or at least many things. And so this is just sort of a tip if you find yourself working with this later. Okay, so here is a really important exercise. If you do no other exercise, do this exercise. You should check for yourself that this model, the model itself, the prior together with the likelihood. So here, the probability of mu and tau given y, that's exactly the joint, the prior times the likelihood. Or sorry, this is the posterior, but for the purposes of this exercise, it's the same as looking at the joint. You want to check that the joint does not factorize. It does not satisfy the mean field assumption. So because it doesn't depend on y for this purpose, we just want to make sure it doesn't factorize across mu and tau. You can look at the joint, you can look at the posterior, you can look at whatever you want. You'll find the joint is easier to work with, but it doesn't satisfy the mean field assumption. So again, we're not making this factorization assumption on the model, we're making this factorization assumption on the approximation. And so that's a really important distinction. And so again, if you do no other exercise in this talk, I strongly, strongly encourage you to do this one, or make sure that you are convinced that this is true. Because if we had to make this mean field assumption on our models, we would not be able to use any interesting models. It would be super boring models. So it's only on the approximation. Okay, so this is the approximation we're making. This is all kind of vague. We're going to see an actual illustration of this on the next page. But here what we're saying is that, remember, we're making this mean field assumption on our approximation. We're saying that our approximating distribution Q should factorize as a distribution over mu times a distribution over tau. And so that leaves off a lot of distributions, including the exact posterior in this case. And so that's the approximation we're making. Now it turns out, because everything here is nicely conditionally conjugate, that you can actually solve to find the coordinate descent steps. This is a nice exercise to derive. Again, if you get stuck, you can check out Bishop's great textbook. But basically what you'll find, again, because everything is set up so nicely, is that the mu distribution, the optimized mu distribution, will be a normal. The optimized tau distribution will be a gamma. And then what happens in coordinate descent, as you expect in coordinate descent, is you just go back and forth between these, solving for sort of what are the parts that define this normal, the mean and variance of the normal, or the parameters of the gamma. And because these aren't our parameters of our model, we want to give them a special name. And so we'll call them the variational parameters. Okay, so let's see this in practice, because I think this will help a lot in terms of illustrating what's going on. Okay, so we have 2 dimensions because we have 2 parameters. So our exact posterior is a distribution over mu, the actual sort of particulate matter concentration, or the log particulate matter concentration, and tau, the variance of our sensors, or the precision of our sensors. And so here, because again, this is a case where we actually have, this ability to just do and find the exact posterior, we could show the exact posterior. You won't have that in general, but here we can do that. And so now what you want to do is you want to look at this and you want to say, okay, well, I got to start my approximation somewhere. And, if we were really focusing on how to optimize things and really focusing on the optimization algorithm, we would want to spend some time thinking, how do we actually initialize this approximation? What's the best way to do that? But in this particular case, I'm just going to say this is how we initialize our approximation. But our approximation is also a distribution over mu and tau. Okay, so now what we're going to do is we're going to do coordinate descent. And first, we're going to optimize in the mu direction. We're going to optimize the mu distribution. So here's my question to you. What's going to change about this picture when I do coordinate descent in the mu direction? Let's break this down. My first question is the green thing going to change or is the blue thing going to change? Exactly, everybody's right. It's blue changes. So green is the exact posterior. It's not going to change. It is what it is. And we're trying to make blue the approximation, in some sense, be closer to green. We want it to be as close to green as possible, really. And that's what we're setting up by making this minimization problem, in some sense. Okay, so blue is changing. Everybody got that right. So now what's going to change about blue? Does anybody have any thoughts about that? Great. Okay, so everybody's saying shift to the left. That's exactly what's going to happen. So the first thing that we want to notice is that definitely this is going to shift to the left. And also what we're seeing with blue here is that it is expanding. And so there are two things here. So one is we're doing coordinate descent. We're changing in mu before we change in tau. And so the only thing that can change is sort of the horizontal axis of this distribution, because we're only changing the mu part of the distribution. And now, because the whole idea here in coordinate descent is that we are trying to get closer to the green, then we should see that the blue kind of gets as close to the green as it can while making horizontal changes. And that's exactly what we're seeing. So it's shifting to the left because green was to the left, and it's expanding to look more like green. Okay, so now let's say we do another step, and now we're doing an update in tau. So now what's going to change about the latest picture that we saw? Great. We're going to see blue again change. Again, like green is just fixed. It's just ground truth. Nothing's going to change. And we're going to see it change vertically because now we're only changing in the tau direction by the nature of our coordinate descent. And it's going to expand vertically so that it looks more like the green. So it's going to shift vertically and it's going to expand vertically. So both of these things are going to happen. And that's exactly what we see in this next step, that again, nothing has changed horizontally because we haven't changed anything in mu, just because we're doing coordinate descent here. And now we're doing this expansion so that blue looks more like green. And then if we were doing coordinate descent, we would just keep doing this over and over again until eventually we reach some sort of stopping point where things aren't moving too much anymore. And this is what we would find in this particular problem. So a couple of points about this. So one, we have focused on coordinate descent in this particular case, but this is the kind of thing that you would expect from any optimization problem, in the sense that you're going to have a blue distribution that's your approximation to your exact posterior. It's going to get sort of closer to it, at least locally, because a lot of these optimization algorithms are local, and so that's something to keep in mind. But at least locally, it's going to do the this getting closer to the exact posterior, and then you're going to find at the end that there's some sort of stopping criterion, things are sort of not changing too much, and then you have your approximation at the end of that, which is sort of the distribution at the end of this procedure. And in this case, it looks like surprisingly good. I mean, this red distribution is certainly not exactly the green distribution, but it seems like the sort of it captures aspects of that. So, we want to be really careful in our wording. So there's a few things that are means and variances at this point. There's parameters that are interpreted as mean or variance parameters. And then separately, there's the posterior we're seeing here, and it itself has a mean and a variance. And so if I talk about the second thing right now, and I say, hey, this is a posterior, it looks like the mean and variance in each direction of the red thing kind of, isn't that far off from the green thing. Now, as we said, this is a case where we are looking at, basically a very simple problem. It's only in 2 dimensions, with very simple data. And so we really want to ask ourselves, well, what does this look like in an actual complex problem with data that's really meaningful, and where you really want to do approximate Bayesian inference? Because there is some issue that, like, the cases where you do exact Bayesian inference, where you can do exact Bayesian inference, might themselves be sort of biased examples of Bayesian problems. And so let's look at a problem where we really want to do approximate Bayesian inference with some real data. So this is an analysis that's due to this awesome economist, Rachel Meager. If you're interested in microcredit, so microcredit is these small loans to individuals in impoverished areas. And the hope is that it helps bring people out of poverty. And then the question is, does that really happen? So if you're interested in microcredit, I really want to direct you to Rachel's paper. She has a few actually on this topic. I'm just going to look at a simplified version of this model so that it's easy for us to look through, et cetera. But again, if you're really interested in the microcredit question, I'll encourage you to check out her papers. But the reality is this is real data. It was collected from 7 different microcredit trials by various experimenters in a number of different countries. So each trial was at a particular site in these countries. And then people want to ask, okay, I have all this data from these different countries. Is microcredit effective in general? And so the data consists of data about a number of businesses, let's say NK in the Kth site, which also happens to be in the Kth country. The number of businesses range between 900 and 17,000 per site. And then the model that we're going to consider here is we want to say, well, does microcredit increase profit, for instance? That's sort of a well-defined question. And so we're going to look at the profit of the nth business at the Kth site. And so here we can call the profit y sub kn, again, for the nth business at the Kth site. And suppose that the profit is normally distributed around some mean that's specific to a site. So this is sort of what you would expect profit to be at a particular site if microcredit didn't exist. And now we want to understand the effect of microcredit. And so we can have a term that consists of first an indicator of whether or not microcredit was given. So these are all randomized controlled trials. And so it was randomly assigned to different businesses, but it's worth keeping in mind, we know the random assignment. So you treat this essentially as a covariate. So you know whether or not this particular business received microcredit. So it's 0 if it didn't, it's 1 if it did. And now this tau k is a parameter very much of interest. It's essentially how much does microcredit influence the profit at this site? And a priori going in, it could be positive, it could be negative. Maybe microcredit hurts people, in which case we want tau to be able to be negative. It could be 0. And then there's some unknown noise for this particular site. And so we can call that sigma k squared. Okay, so now we don't know mu k, tau k, and sigma k squared. So they're all going to be parameters of this model. And so what we can do is we can put priors and hyperpriors on them. Again, I wouldn't pay so much attention to all the details of this model. What's really important here is just that this is a model. It has some unknowns, that those unknowns will tell us about microcredit, and we're interested in learning about their posterior. So here, one potential thing we could do is we could say we have a normal prior. So for each site, there's the sort of site-specific profit without microcredit, and then the effect of microcredit. And we'll say that's normal around some global profit mu and some global effective microcredit tau. So if there was only one parameter that we cared about in this model, it's probably tau without a subscript, because that's like the global effect of microcredit. Maybe it's helpful, maybe it's not, we want to know. And this normal model lets these things take on negative values or zero values or positive values. And then C is some unknown covariance. Okay, so again, we don't know the sigma squared. We can put a gamma, an inverse gamma on it. We don't know mu and tau. We can put a normal on those. And it turns out that the separation in LKJ prior is a nice prior to put on covariances. And again, I won't get into that, but it's a cool thing if you're curious. Okay, this is all to say now we have a model, and it has many parameters, or at least many more than the previous slide. So now you have mu k and tau k for every site. So that's already 14 different parameters. You have mu and tau, you have all the parameters in C, you have sigma squared across every site, sigma k squared. So we have quite a few more parameters, and certainly we can't just plot our posterior anymore. We're gonna have to look somehow individually at means and variances of these different posterior parameters. Okay, and so what we're going to do is we're going to run variational base to get our approximate posterior, and then we're going to report posterior means and variances, approximate posterior means and variances for each of these parameters. And so a first question we want to ask ourselves is, do we need to check the output? If I just ran variational base and I told you that the mean effective microcredit was 5, or like $5 US purchasing power parity, imagine it's in the correct units. Do you trust me? Okay, I hear a no. And this is the reality. We don't have a proof right now. that this is definitely giving the right answer. And so at least it seems like we would like to check the output. We would like to check if this is going to be doing the right thing. And so immediately the next question is, well, how do we check the output? Because now we don't have access to an exact posterior. You can check this for yourself, but this is no longer a conjugate model where you can just calculate everything in closed form. This is a real problem where we really need approximate Bayesian inference of some form. And so I'm going to tell you what I'm going to do for the moment, but perhaps you can be thinking in the back of your head, what else could you do? What I'm going to do for the moment is I'm going to say, let's compare against Markov chain Monte Carlo. If they agree, then at least it seems more likely that they're both right. This is another approximate Bayesian inference algorithm. It pretty much, operates on a completely different mechanism than variational Bayes. And if they don't agree, well, there's a lot of checks for Markov chain Monte Carlo. And so at least if it's run long enough, there's reason to trust it. But then it's tough. Like, how do we know that this is working? Okay, so anyway, that's what I'll do in the meantime, but it's an interesting question that we'll have to revisit and keep coming back to. Okay, so what I'm going to do here is I'm going to say I'm going to run mean field variational Bayes for all these different parameters, to get my approximate Bayesian posterior, and I'm going to run Markov chain Monte Carlo, and here I'm treating it as sort of a ground truth. And then we're going to compare, in this case, let's say the posterior means that we get from each of them. Now, running, in this case, Markov chain Monte Carlo with modern automatic software for this problem takes on the order of 45 minutes, whereas mean field variational Bayes optimization takes way less than a minute. And so this is why we'd like to develop variational Bayes. It's so much faster, and that can make a huge difference, especially as we get into larger problems. This isn't even like that large of a problem yet. But this is why we'd like to get beyond it. And I think the question in the chat is really getting at exactly this. If we use MCMC, then what's the point of approximating? I don't think you missed anything at all. I think this is exactly the question that I'm getting at. We don't want to be comparing to MCMC in general. Now, I want to be clear, MCMC is also an approximation. So it's more like if we use MCMC, what's the point of an additional approximation, right? Yes, exactly. Like we need to ask, how do we get to an additional approximation where we can trust it, where we know that we're getting an answer and we don't have to compare it to MCMC, because as soon as you run MCMC, you've got the cost of MCMC. So absolutely, I think this is exactly the question we want to be answering. But we haven't answered it yet, so let's compare to MCMC for now, because for various reasons, we might trust its output in this case. And this looks good. So here we're seeing that the mean field variational Bayes means, the posterior means returned by mean field variational Bayes. We get one vertical coordinate for each parameter. And we plot the horizontal coordinate as the mean returned by MCMC, and these agree. These agree really well. And so this is looking pretty good. It's looking like we're getting some good results here. Okay, let's look at some more real data examples. So here's one from Criteo released this very large data set about online ads. So they're interested in something like conversion prediction. So if a customer clicks on an ad, do they then buy a product or join an email list or something like that? And a very common thing we might also be interested in is how predictive of conversion are different features, like maybe different parts of the ad. Now, even if you're not interested in online ads, this is a very common type of problem. You might be interested in forestry and saying, oh, we really want to understand what's parts of the forest or maybe at risk or have different types of leaf cover. And we want to know how predictive various features are of that. So many problems form this kind of thing where we want to do some kind of prediction. We want to do it well, but we also want to understand how features, are involved with that prediction. And so a common model here, especially if we want to have some kind of understanding and interpretability, is a logistic generalized linear mixed model. This will let us tell us sort of, how our features are, influencing our output. Now, here's the rub. This is actually a huge data set. You can easily get into the millions, if not billions, of data points. And MCMC just cannot handle that. It's really beyond something that you would run in a reasonable amount of time. And so we're going to take a subset, just 62,000 data points in order to compare to MCMC. But, already we're seeing the issue, right? That like you can't even run MCMC at the sizes of data points or the numbers of data points that we would like to run. And so we're seeing certainly why we'd like to get beyond it. Okay, so let's look at this Criteo online ads experiment. Now, before we get into comparing mean field variational Bayes versus MCMC here, I want to start by saying, something you might have been thinking this whole time is, why don't I just use MAP? So let me remind you, so MAP is a maximum a posteriori estimate. On its own, it's just going to give you a point estimate. It's just going to give you a particular value of the parameters theta. You could use it with Laplace to get an uncertainty as well, but let's just look at the point estimate for the moment. Now, the thing about MAP is you're just maximizing the posterior and the parameters. And so it's completely equivalent to maximize the joint distribution between the data and the parameters in the parameters, because y doesn't come into that maximization. And that's just the prior times the likelihood. So here you don't have to deal with the normalizing constant at all. You just maximize this function. And so that's like super easy to do. It requires like very little work on the part of the practitioner. It requires extremely little computation. Here it just takes 12 seconds. It's super fast. So why don't we just use MAP all the time? Well, there are various reasons that you might care about the posterior mean. So let's suppose that you do. Now, in this particular case, what we're going to do is we're going to do a similar thing that we plotted on the last page. So first, we're going to look at all the global parameters except for this one called tau. On the horizontal axis, on the left, we have the MCMC, the posterior mean returned by MCMC for each of these parameters. And on the right, or sorry, on the left, but the vertical, we have the MAP estimate. Now, of course, a mode is not the same as a mean, and that's basically what we're going to be illustrating here. But suppose you wanted to use MAP to try to get at the mean. Well, these are like, some of these values are kind of okay. One's a little bit off. But now let's look at tau. There's this global parameter tau that sort of controls essentially the local parameters, as we're going to see in a moment. And you can see that MCMC estimates its posterior mean to be about 0.8, and MAP estimates its point estimate to be about 800. So that's, a few orders of magnitude off. So if you really cared about this value, you're pretty far off. And actually, more to the point, it turns out this controls, again, the local parameters, things like maybe how effective are the different advertising agencies or the different types of ads. And as a result of getting tau off, we see that MAP basically just gives all the local parameters the same value. And so they're just completely off. There's no difference between them, whereas MCMC clearly sees a difference between that. And if you want to get that information, you're just out of luck with MAP. And so this is also say that like MAP doesn't seem to be getting at what we want if what we want is things like posterior means. Okay, well, let's try mean field variational Bayes. In this case, it's actually not much more expensive. It's only 57 seconds. That's not too bad. And it turns out it just gets everything really well. So here we're seeing all the global parameters, which we can finally plot on the same scale because there isn't one that goes off by orders of magnitude. And so we're seeing the mean field variational Bayes approximations of the posterior mean compared to Markov chain Monte Carlo approximations of the posterior mean. And these look really good. They're very close. We're seeing the mean field variational Bayes approximations of the posterior mean for the local parameters as well. And again, they're very close to the MCMC approximations of the posterior mean. And again, why don't we run MCMC? Well, again, it struggles even beyond this data set, but even for this data set, even for just 62,000 data points, it takes on the order of 6 hours. And that's already just much longer than MAP or mean field variational Bayes. Okay, so this is pretty exciting, right? We're seeing, we wanted to find a method that was fast and accurate, and certainly MAP doesn't seem to be very accurate here if what we care about is posterior means. And at least in these examples, so we've gone through 3 examples now, mean field variational Bayes seems to be very accurate empirically at getting posterior means versus MCMC. So we're using MCMC as ground truth here. And so that's pretty exciting, and it's much, much faster. And I think it's actually pretty amazing that you can make this extremely strong mean field variational Bayes assumption, and yet you can get out what seems to be some pretty good approximations in cases where these are very complex models and they have complex dependencies. Okay, now before we go on, I just have to say, we're still talking about like why use mean field variational Bayes. So we already see that there are some cases where empirically it seems to give good point estimates. We are checking it in some way, and the only way that we could think of so far is to look at exact posteriors or like an MCMC approximation. And, if you can think of anything further, that's the kind of thing we're thinking about in the back of our minds. But while we're talking about why use mean field variational Bayes, I think that the elephant in the room is topic modeling and topic discovery. So there's this just extremely influential model called latent Dirichlet allocation. And the idea here is that you have a huge corpus of text. Text is just ubiquitous these days on the internet, but also just in terms of like the text that people are generating at their jobs, the text that people are generating in medical applications, the doctor's offices, and so on. And so there's so much text these days, and we want to be able to make sense of it, to understand what are the themes, the topics in it. And latent Dirichlet allocation does that. And I feel like just every time I turn around and then look again online, it has more citations by like a ton. And I think I looked yesterday or something, and it had over 33,000 citations, but maybe tomorrow it'll be 34,000. I mean, this is just an incredibly influential model. And so if there was literally nothing else that mean field variational Bayes was used for, this would already be enough to make it, just extremely influential, something that people are just using very widely. Okay, so we've talked about why to use it. It seems like empirically in a number of cases, it works well, at least according to our notions of working well that we've explored here. And now I want to spend a little time thinking about, okay, well, can we trust it in general? I mean, as there was this great point in the chat, we don't want to run MCMC every time. I mean, we can't. We literally can't. We've already talked about these data sets that are just much bigger than we can handle, typically with MCMC. And you can make a special MCMC algorithm for every new thing that comes along, but it would be really nice to just have something that runs really fast at scale that you can trust. And so the question we want to ask ourselves is, well, can we trust this? So based on what you've seen so far, do we know that every time mean field variational Bayes, or variational Bayes in general, returns some posterior mean and variance approximations, do we know that those are correct? Okay, so let me narrow that question down. Let's suppose that I show you a posterior variance approximation from mean field variational Bayes, let's say. Would you trust that based on what we've seen so far? What have we seen so far to support a posterior variance approximation being good or bad? Have we seen anything? Yeah, I guess we haven't. I mean, we sort of have. We saw that 2-parameter model. So if we go back to the PM 2.5, we actually did look at like the full distribution there instead of just a point estimate. But you'll notice that when we talked about the microcredit example, or when we talked about the Criteo example, I actually didn't show you posterior uncertainties. I didn't show you posterior variances. I actually just showed you posterior point estimates and means. And so we actually haven't checked on the quality of posterior variances in any of these cases, sort of the width of the posterior. And that's really important. We really care about that because, if you're going to say, hey, I need, I'm going to invest in microcredit, and I think that it raises incomes by, $1,000 US purchasing power parity every week. That sounds really great. And is it 1,000 plus or minus 1? In which case, yeah, like we know that it's really helping people. Or is it 1,000 plus or minus 10,000? In which case, maybe half the time it bankrupts people, and maybe that's not a really good thing that you want to be investing in. Okay, so let's see if we can actually get these variances right as well, these uncertainties, which we motivated in the beginning with all of our applications. There are lots of applications that care about uncertainties, so let's talk about uncertainty. Okay, so here we have the KL divergence. This is just reiterating what is the KL divergence that we're optimizing. So it's the particular direction used by variational Bayes. And we have our assumption, our mean field variational Bayes assumption written out, this factorization assumption, that this Q factorizes over these little components, theta j. Okay, so let's consider, again, a super simple example. It's an exact Gaussian. So suppose my exact posterior, my 2 parameters are theta 1 and theta 2, and my exact posterior is a Gaussian. Why would we even care about an exact posterior that's a Gaussian? Well, there are a couple of reasons. So one is in conjugate linear regression, you're going to get a Gaussian. Now, of course, again, we're not going to use approximate Bayesian inference in a conjugate problem, but there are a lot of problems that are close to conjugate linear regression, and maybe we expect that they have a somewhat similar geometry. Another example is that there's this thing called the Bayesian central limit theorem. And it says roughly, and you have to be a little bit careful here, but roughly as I get more and more and more data about a particular parameter, the posterior over that parameter is going to look more and more and more Gaussian. And so for all of these reasons, we think that Gaussians or shapes like Gaussians come up reasonably often. And so this is not like, you know, a totally made up example. This is kind of a realistic shape that you might encounter in real life. And of course, it would be higher dimensional than two-dimensional, but you'll see that the conclusions we make here apply to more than 2 dimensions. Okay, so this is a case where if you're clever and use the precision, you can very easily derive the mean field variational Bayes coordinate ascent steps. So here I'm saying coordinate ascent, I'm saying that as CA. I said coordinate descent earlier, it's just how you think about it, right? You're minimizing the KL, but you're maximizing the L though. So, you know, you're doing coordinate something. And of course, you don't have to optimize in the coordinates, but here you can do it very easily. And in fact, you can go beyond that. Once you've derived these steps, you can actually derive exactly the mean field variational Bayes approximation. You don't even have to iterate. You can just write it down. And I think this is another really nice exercise to do. Just make sure that you can write this down. You can figure out what is the exact mean field variational Bayes approximation. No optimization algorithm needed. You just write it down. And this is it. This is the mean field variational Bayes approximation here. And so the mean, actually, the posterior mean is exactly right, the approximation for the posterior mean for mean field variational Bayes, but you can just immediately see that the variance, you know, the width of the distribution is way off. The width of the green thing is way larger than the width of the red thing. And the red thing is meant to be approximating the green thing. So we get these underestimates of variance. That's actually sort of like the worst direction, right? Because if you are saying, hey, you know, I want to be really careful and conservative and not rush into a decision, that's like the opposite of what you're saying here. You're saying, oh, I'm super confident. I'm going to invest a ton of money in microcredit, or I'm going to invest a ton of money in this other thing, even though I don't really know enough to maybe do that yet. So you're sort of rushing into decisions as a result of this. And in fact, you can be sort of arbitrarily overconfident just when the exact posterior is very correlated. And the issue is that you don't know the exact posterior. So it could be very correlated and you just don't know because, again, you don't have access to it. This is sort of the only information you have about it. And so if you only saw the red thing, you might think, gosh, I'm super certain about what's going on. I have very little uncertainty, when the reality is the green thing, and perhaps you should have a lot of uncertainty. And then, of course, by construction, you don't get covariance estimates because you're making this factorization assumption. And so you can't get covariance estimates. And so let's see how this comes up in real life. So let's look at this microcredit example again. So before, I had a point for each parameter, and for each parameter, I plotted the MCMC estimate of the point estimate, the mean, and the mean field variational Bayes point estimate of the mean, and we compared them. And so let's do the same thing now, but for standard deviation. So here, again, for every one of the parameters, we have a point. Its horizontal value is the MCMC estimate of the standard deviation, the posterior standard deviation for each parameter. And the vertical value is the mean field variational Bayes estimate. And you see that there's this x equals y line that's in black. And so mean field variational Bayes is systematically underestimating uncertainty. Now, it turns out it doesn't have to underestimate uncertainty. It can overestimate it as well, but that's kind of even worse because you just don't know what's going on. And in general, we tend to see empirically that it underestimates uncertainty. And this has a real empirical consequence. So suppose that I'm interested in tau, again, the microcredit effect. How much is microcredit helping people, if at all? And I find perhaps that the posterior mean is something like $3 US purchasing power parity every 2 weeks. So it's helping people, it's positive. And then maybe I find that the standard deviation is 1.83 US purchasing power parity. And so the mean is 1.68 standard deviations from 0. Now, something I might have done is I might have gone into this problem saying, hey, if the mean is positive, the mean effect, you know, how much is microcredit helping profits? If it's positive and it's more than 2 standard deviations from 0, and it's like substantive enough, you know, that it's really helping, then I'm going to invest in microcredit. I'm going to, you know, go out and make this my cause, and I'm going to, you know, really make this happen. And here I find that in fact the mean is not 2 standard deviations from 0. So I'd have to either gather more data or try to understand, are there certain covariates of households that influence whether microcredit is effective? You know, I'd have to go back to the drawing board and do some more social science. But here, what's going to happen if I use mean field variational Bayes is I'm going to underestimate the uncertainty. And because I underestimate it, I'm going to erroneously think, I'm going to make the error of thinking that the mean is more than 2 standard deviations from 0. And I'm going to rush into a decision that is not warranted by the actual Bayesian posterior. So to the extent that we trust the Bayesian posterior, this is just giving us a different answer, a bad answer. It's not giving us the actual Bayesian posterior. And in fact, we see this in other areas as well. So this is the Criteo online ads example. And here, again, we're looking at standard deviations rather than means this time. And for each of our parameters, we're seeing that mean field variational Bayes is very much underestimating the standard deviation, the posterior standard deviation. If we think that MCMC is doing the right thing, and there are various checks that make it likely that it is here, then it seems like mean field variational Bayes is just off, that it's just not, getting these correctly. Okay, what about means? We've talked about standard deviations now. But do we know that mean field variational Bayes gets posterior means right? Well, let's think about what we've done so far. I've shown you 2 empirical examples. I've shown you the posterior means being correct on the Microcredit example. I've shown you the posterior means being correct on the Criteo online ads example. And we showed also this sort of, almost toy example of PM 2.5, the particulate matter. And so I guess the question, the sort of meta question is, if I show you 3 examples of something working, does that mean that it works all the time? And hopefully the answer is clear that it is not a proof that it works all the time. I mean, it's certainly some evidence that it's useful, but it's not a proof that it works all the time. And perhaps we might look at some examples where it does not work all the time. And so this is a model for relational data with covariates. So relational data is like data on a graph. Bailey Fosdick does some really excellent work in studying graphs and networks. And of course, we have giant network data nowadays. You look at social networks, but also environmental networks, transportation networks, and you can easily get more than 1,000 nodes. But again, there's this issue that if you have more than 1,000 nodes, Markov chain Monte Carlo takes forever. You don't want your algorithm to take more than a day because you're going to have to iterate on this algorithm, and it's going to take a while. And so here again, we're looking at mean field variational Bayes, estimates of posterior means versus MCMC estimates of posterior means. And it seems like they're not quite on that X equals Y equality line. And in fact, we can look at particular parameter values here and look at 95% credible intervals. So this is a little bit different than what we've been looking at now. Before we were looking at sort of variances, but if something isn't symmetric, you might want to look at credible intervals. So where is 95% of the mass in your posterior, and that's what we're seeing. So the point is a point estimate in black here for each parameter on the horizontal axis, and then the vertical is the line is the 95% credible interval. And what's interesting is you're seeing that mean field variational Bayes means estimates are sometimes outside of the 95% credible interval. And so that's problematic, right? Because if you're using this to make decisions, then that suggests that you would make a different decision, that your mean really is outside where the range of values that might be an acceptable place for that mean. If you assuming you care about the Bayesian posterior. Okay, and now another question we might ask is, well, maybe there are certain types of problems that mean field variational Bayes is good on and certain types of problems it's not. And so if we just knew those in advance, we could just, sort of apply mean field variational Bayes only to those types of problems. And so let's suppose that we want to predict some measure of performance in college, at university. So like grade point average is a common measure of performance for an individual. So let's say N indexes an individual. And then maybe in order to do that, we might collect standardized test scores, like maybe some kind of test people took in high school. So there might be some tests that are common across our population. So like if we had a US population, at least before this year, SAT and ACT might be an example of that, but it could be some other population. But it's often the case also that there are regional test scores. Even if we had a global population, there'll be regions, certain countries have their own tests, and so we might want to take those into account as well. And so we might come up with a normal model where there's some linear component specific to like a general test scores, and there's some linear component that varies by region. And so it's indexed by KN, which is, let's say K is the region. Okay, and then we have some priors, and this is all to say this is a model. This is a model with parameters. Parameters we're interested in learning that we have some posterior over. And so what we can do is we can simulate data from this model. So we know that there's no model misspecification. Our data is exactly from the model that we are specifying, so we're not even messing around with that. We get 3 data sets. Each has 300 data points. And now we're going to plot the MCMC mean estimate of a particular parameter for each data set versus the mean field variational Bayes mean. And so we have that here. And this is across data sets for the same parameter, whereas before we were plotting for a single data set, different parameters. So it's a little different from before. But based on this, you might think, gosh, mean field variational Bayes works well for this type of model, because look, the means agree between MCMC and mean field variational Bayes. But now suppose I simulate data from, 100 different data sets, and I find that a lot of the means now don't agree. And so it doesn't seem like I can just conclude in this particular case, that this model is good for mean field variational Bayes. Okay, so I'm gonna leave off here. I'll just finish up on this slide. I think we want to ask, what is the issue? In particular, here are your options. It could be my implementation. Maybe the implementations that I used in these examples are bad implementations. Maybe there's a bug in the code somewhere. Maybe it's my approximating algorithm. Even if my implementation is exactly correct, we know that optimization is a little challenging. Maybe I just used a bad optimization algorithm. Maybe it's the mean field part of mean field variational Bayes. Maybe it's variational Bayes, maybe it's something else. And so this is where I want to leave you with a question for next time, because we'll take up this question again next time. What is it? Can you rule out, based on the information that we have right now, whether the implementation is the issue? Could that possibly have always been the issue? Could mean field variational Bayes always give you the exact correct answer, but it won't, of course, if there's a bug? Can you rule out the algorithm? Can you figure out at what level this issue might be at? And so I'll just leave you with that question to think about for next time. Again, all of the slides will be distributed to you. They'll also be up at my website. And I really, really encourage you to think about some of the exercises in the meantime, because I think that will be helpful as well. Okay, great. I'll leave us on that cliffhanger, and I believe I will catch you 2 days from now to talk more about where we have left off. Thanks very much.